Hi, I'm Edenna Hiletework, and my project is on improving a VGG19 machine learning model in the identification of skin cancer. In the early stage of skin cancer, stage 0, such as melanoma in situ or carcinoma in situ, the tumor is localized to the area of the skin where it has originated and has not yet spread to nearby lymph nodes or other parts of the body. It is difficult for clinicians to differentiate when skin cancer is in these early stages, which results in false positives or false negatives. As seen, this image is clearly benign, meaning non-cancerous, while this one is malignant or cancerous. Now, it is clearly apparent which of these images are malignant and benign, but it is less obvious to define this image in the middle due to its less distinct features. It is malignant. According to the American Cancer Society, other systems such as CT scans, MRIs, or biopsies are commonly used to identify cancers, but result in interpretation errors by clinicians. Furthermore, visual screenings are less accurate for non-melanoma skin cancers, such as basal cell carcinoma or squamous cell carcinoma. Regardless of experience, the human eye is subjective to inconsistency and error. There is always room for error and confusion when interpreting an image due to its asymmetry, irregular borders, or color variation. Cancer has been identified through dermoscopy for many years, and it is usually successful but can result in error. Around 1 to 10% of cases result in false positives, where a benign lesion is mistaken as malignant. These are cases when another skin irregularity, such as a mole or rosacea, is confused for cancer, while the other 5 to 25% are false negatives, which is when the lesion is in fact malignant but overlooked. A 2021 study performed on 5,000 cases revealed that the sensitivity for melanoma was 88%, basal cell carcinoma as 78%, and squamous cell carcinoma as around 70%. Traditional methods of cancer identification involve numerous limitations. For example, conclusions on whether cancer is present can vary between pathologists depending on levels of experience and exposure, which can result to bias. A tool that has gained prominence in cancer identification is machine learning. A group of researchers at Stanford University performed a research study with multiple dermatologists of different levels of experience, from junior chiefs to physicians, and a deep-trained convolutional neural network, which succeeded to demonstrate that the neural network can outperform these dermatologists from 12 different facilities. The respective sensitivity and specificity of lesion classification by the dermatologist was 67.2% on a 95% confidence level, ranging from 62.6% to 71.7%, and 62.2% ranging from 57.6% to 66.9%. In comparison, the trained CNN achieved a higher sensitivity, exhibiting 82.3%, ranging from 78.3% to 85.7%, and a higher specificity of 77.9%, ranging from 73.8% to 81.8%. While these models are exceptional in terms of classification, there is still room for refinement. Researchers have developed grayscale techniques. A study centered around COPRA classification utilized grayscale imaging techniques to improve the accuracy of a machine learning model. In conclusion, the COPRA in various stages were categorized using combined features of GLCM and TLGLCM, which expressed a higher accuracy in COPRA classification, outperforming other classifiers. This indicates that combining grayscale imaging techniques increases the accuracy and other statistical parameters of machine learning algorithms in terms of classification. My goal throughout this project was to develop a skin cancer identification system for skin cancer images as RGB images, altering the machine learning algorithm utilized for skin cancer identification as RGB images to grayscale images, and improving the accuracy of a skin cancer detection model. My hypothesis was that images on a grayscale will produce a higher accuracy compared to RGB images of skin cancer. Over the course of this past summer, I was responsible for developing my understanding of machine learning to effectively execute a system that was able to interpret images of skin cancer. The role of my mentor was to provide me with a trained and readily available data sets, as well as insight on machine learning algorithms and recent pieces of literature to fortify my familiarity centered around machine learning and cancer. I went through a process of collecting images, processing them, training the classifier, while the algorithm carried out image detection and classification. Lastly, I converted the images to a grayscale. My mentor was able to help me find a data set containing 330 images, which then increased throughout techniques exhibited in Part 2. Afterwards, I was also provided with the necessary code for the model. The model itself detected and classified the set of images. Lastly, I repeated this process for the images on a grayscale. When selecting a data set, it was important that there was a minimum of 30 to 50 samples of cancer that I was interested in to ensure proper validation. There are many publicly available data sets, such as the TCGA database, which is listed above, or one that I found on GitHub. The database I utilized was recommended by my mentor and was compiled by a military institute. It contained a total of 330 images, which I transferred to a separate drive so that the images were in a usable format for coding. The images are then separated into a larger file labeled as benign and malignant. From the data sets, all of the images are rescaled to 244 by 244. Traditionally, to create more data, augmentation techniques are executed. Images can be resized, inverted, cropped, or rotated through different Python commands, which are then interpreted by the system as being an entirely new image. Now, because my system was trained on RGB images, the accuracy was able to increase through these augmentation techniques for the grayscale images. VGG19 is categorized as an image classification system, and I implemented it into my system for image recognition. I used VGG19 rather than VGG16 because the layers are more complex and deep, which contributes to higher accuracy and higher precision when identifying images through the complex convolutional layer, max pooling layer, and fully connected layers. A machine learning study performed on skin cancer slides produced a 98.4% accuracy with a PH2 cancer database while utilizing a deep CNN. There are 16 convolutional layers grouped into 5 blocks. After every block, there's a max pooling layer that decreases the size of the input image by 2 and increases the number of filters for the convolutional layer also by 2, which overall reduces the spatial dimensions while preserving the most important features. It ends with the fully connected layers, which is responsible for classification. Images are then converted into arrays. Arrays are linear data structures where all of the elements are arranged sequentially. This is a collection of elements of the same data type stored in memory locations as values. The arrays are labeled as 0 being benign and 1 malignant. After running 10 epochs of the image, they are detected and classified as cancerous or not cancerous, and a bounding box is presented over any distinct features. To construct this code, I utilized a Python library, which allowed me to do commands such as importing the file, and I also used OpenCV, which helped process the images as well as recognizing them. RGB are the color channels initially interpreted by the system. It consists of 3 colors, red, green, and blue, which produces others through mixing. Grayscale varies between shades of white and black, where every pixel has a different intensity value. The files containing these images are all converted to grayscale images. I ran 2 of the same algorithm, except one was altered to output and interpret the files as grayscale images as displayed on the right. The algorithm was able to measure accuracy loss, validation accuracy, and validation loss, as well as how long each epoch took. The loss highlights how poorly the prediction matches the actual value displayed by the RGB and grayscaled images. I focused on the last epoch because it's a representation of the model's final iteration where it was able to capture the most refined patterns from the data. To avoid overfitting, I ended the trial at 10 epochs because it would prompt the model to memorize data rather than observing its patterns. The accuracy graphs of the RGB images are positively correlated while the loss for each epoch is negatively correlated, indicating that the system is improving. The graph for the grayscale images exhibited the same characteristics regarding the relationships between epochs, loss, and accuracy, but the grayscaled images achieved a higher accuracy in the last epoch compared to the model used for the RGB images. The objective of the study was to illustrate the efficiency of a machine learning model utilized in the identification of skin cancer. A VGG19 model was tested on a total of 330 images, which increased and belonged to two classes, benign and malignant. The algorithm defines the image as either being benign or malignant and displays the image. My results supported the hypothesis that the grayscaled images would achieve a higher accuracy and a smaller loss. The data set was distributed evenly between benign and malignant as reflected by the figure, so training data was an appropriate determiner of the model's performance. Some limitations I encountered during this project was the limited amount of storage. Libraries such as TensorFlow, OpenCV, and NumPy consume a lot of space, as well as data sets and the augmented images. This restricted the quantity of the training data set. Another limit was the model's ability to identify corrupted images. The images in the data set I used were of a higher quality and were already denoised. Future research for skin cancer could be done by developing a mobile application of this algorithm. Pathologists currently utilize phones for anatomic pathology such as microscopes. Advances can be made including image analysis, alternative light sources, and opportunities for patient-client engagement. Phones could also be utilized to translate the images to hyperspectral scale, mimicking a hyperspectral camera, which can later be used for classification to monitor whether the accuracy of the model would increase. Hyperspectral images are images that capture information across a wide range of wavelengths in the electromagnetic spectrum, spanning from visible, near-infrared, and the thermal infrared range. A research study established that a new method of using hyperspectral imaging and a deep learning diagnosis model to classify and diagnose esophageal cancer using a single-shot multi-box detector. The accuracy of the results when using the RGB image was 83%, but while using the spectrum data, the accuracy increased to 88%. This study reinforces the potential of machine learning in the field of pathology and the uncertainties revolving around cancer diagnosis that can be minimized with the assistance of improved machine learning models. First off, I'd like to give a huge thank you to Mr. DeGroat for his endless support and guidance during this entire research process. My mentor, Ms. Meenal, for helping me conduct this project, as well as her brilliant recommendations. My parents for their persistent insight and advice, and lastly, for the Marine Chem class of 2025 for making the past years at Bellarmine more memorable. Here are my references. And I will now be taking questions. The question was the coding done entirely in Python? And yes, it was. The question was, how did I find this project? I was working with a mentor at the University of Washington, and she first suggested that we did a project with H&E images of breast cancer, but it was hard to translate those to grayscale. So she suggested that we move to skin cancer, which is more present on the skin and easier to translate to grayscale. The question was, how did I start working with the mentor at UW? Pretty much I went through a whole process of sending like multiple emails to different researchers that I found through like journal articles who were currently researching like the crossovers between machine learning and cancer. And then I came across her and she responded to my email. And yes. The question was, can this algorithm be used for other forms of cancers? Yes, but it would need to be altered so that I could recognize patterns from those images. In the back. The question was if I accounted for the image quality. So the images I used from the database were already like altered and perfected so that it would be easier for the algorithm to identify, which was also mentioned in my limitations because I didn't use any lower quality images. Sorry. Any other questions? And next up we have Connor Mao and Jameson Cosgrove.